Welcome back everyone. In this lecture, we will actually give an alternate definition of the sign map. So, first let us recall how we defined the sign map in the earlier lectures. So, the sign map is associated with the symmetric group Sn. Okay, let us recall what it is. So, the symmetric group Sn is a group of permutations of this 1 to n, okay, which we denoted by in. So, this is denoted as 1 to 1. So, we have this sign map, so which is denoted by SGN or SIGN and so on. So, which is the map from Sn to plus or minus 1. So, this map is very important map. So, the way we defined actually we used the action of Sn on Rn, and then we realized each permutation with this permutation matrix associated with that permutation, and using that interpretation we have actually defined this map. Okay. So, let us briefly recall how this Sn acts on Rn, and then how one can use that action to define this sign map. Okay. So, note that. So, if you start with some sigma in Sn, so then sigma acts on Rn by permuting the coordinates by sigma. So, what is the meaning of that? So, that means if I take sigma and then if you actually act it on this V1 etc. Vn. Okay. So, basically, so let me actually interpret in terms of maps. Okay. So, you are defining a map tau that is from Sn to this GLN of R. So, the map is given as follows. So, given sigma, you associate what is called this tau sigma. So, what is this tau sigma? So, tau sigma simply you fix a standard basis of GLN of R, sorry, standard basis of Rn. So, let us call it V1 etc. Vn. So, this is the standard basis. So, the standard basis of Rn. So, that means Vi is just 1 0 comma 0 and so on, and Vi is a 0 comma 0 etc. 1 comma 0 0 etc. So, then each element of Rn can be written as linear combination of this Vi's. So, that we know. So, now what this tau sigma does, okay, this tau sigma is just simply permutes this Vi's. Okay. So, tau sigma of Vi, you define it to be V sigma I, okay, for each I from 1 to n. So, now you extend this tau sigma linearly, extend this tau sigma linearly to Rn. So, then it is clear that this tau sigma defines invertible linear transformation on Rn. So, in particularly this lives inside GLN of R. Okay. So, now you can easily see that when you take tau sigma and sigma dash, then that will be indeed mapped to tau sigma compositions tau sigma dash. So, this is something we already verified. I will leave it you to verify, okay, as maps. So, you can verify that tau sigma sigma dash is same as tau sigma composition tau sigma dash. So, now what this says? This says that this map, that sigma goes to tau sigma, it is a group homomorphism from Sn to GLN of R. Now, with respect to the standard basis, if you write down the matrix of this tau sigma, and let us see how it looks like. Okay. So, you take this standard basis V1 etc. Vn. So, let us call it B. So, then this tau sigma with respect to this standard basis, you can see that this is going to be exactly, you take this identity matrix. Okay. So, the identity matrix we are going to denote it by, so this identity n by n. So, which you use this uh, row notation. Okay. So, basically it is actually, so I am going to use this column notation. So, you call it E1 etcetera En. So, where Ei is nothing but this ith column of this identity matrix, which is 0 etcetera 1 etcetera 0, where this 1 appears at the ith place. So, then it is clear that the tau sigma of B is nothing but E sigma of 1 etcetera E sigma of n. Okay. So, basically you take this identity matrix and you permute the columns with respect to sigma. Okay. Then that is the matrix that you are getting here. So, then what we did, we defined this sign of this sigma to be exactly equal to the determinant of this tau sigma with respect to this matrix. Okay. So, you know that the determinant of this tau sigma with this is independent of the basis that you choose. So, in particularly this is actually well defined. So, the sign is defined to be the determinant of the permutation matrix associated with the sigma. Okay. So, this is called the permutation matrix. So, this is called permutation matrix associated with sigma. So, this is the way we actually defined the sign map. Okay. So, this already tells you that somehow like determinant should be get involved in defining this sign map. So, there is no other option defining the sign map. Okay. But if you take some standard algebra books, okay, sometimes some different approaches are used in order to define the sign map. Okay. So, I will explain one such method now. Okay. This is I took it from Dummett and Foote, but implicitly somewhat the determinantal properties are hidden in the definition of that sign map. Okay, that is defined in Dummett and Foote. Okay. I will also mention the, some other way of defining this sign map, okay, using some other identities. But anyway, let us first see what Dummett and Foote does. So, this is the way we actually defined. Okay. So, we wanted to use the action of the symmetric group on Rn, okay, and then you take this group homomorphism from Sn to Gln of R given by sigma goes to tau sigma. So, then we defined this. So, this is actually an injective map, that is something we also verified. So, this tau is injective group homomorphism. So, now using this one can verify that this one can define that the sign of sigma is nothing but determinant of this tau sigma. So, then we also verified that the sign of any this transposition is nothing but -1, okay, and sign is indeed group homomorphism because it is composition of two group homomorphism, one is tau and another one is this determinant. Okay, both are group homomorphism. So, composition of group homomorphism is again group homomorphism. So, basically the map is defined from Sn to Gln of R. So, this is the map tau. Okay. Then from Gln of R to this plus or minus 1, you have this map determinant. Okay. So, not exactly this. So, we need to go to this the range will be any positive real numbers or any non-zero real numbers actually. But when you compose this tau with determinant of Sn, so this will be lying inside plus or minus 1. So, this is something we can see from the definition, because these permutation matrices will have determinant plus or minus 1. So, this is something we have already done. So, now we are going to see some alternative definition using some polynomials. Okay, for that what we need to do, we introduce this notation called delta. Okay. So, it is actually a multivariate polynomial. So, which is given by product of these monomials, product xi minus xj, where ij varies over I less than j from 1 to n. Okay. So, what we do, we first take, so this n is fixed, this n is coming from the natural number. So, given this n, so we take this x1 etc. xn, these are all commuting variables. You take these commuting variables x1 etc. xn, then consider this polynomial which is multivariate polynomial which is in x1 etc. xn. So, that we call it delta. So, this delta is somewhat very important. So, this sign of any permutation can be defined using this delta. Okay. But before introducing the definition of sign map using this delta, so let me tell you where this actually delta comes from. So, this delta indeed comes from the determinant of Van der Waals matrix. Okay. So, here is the motivation. So, again there is no other way to actually define sign without involving the determinant, okay, because determinant and sign maps are very much closely related. So, whatever definition that you see in the literature, they all somewhat implicitly use the knowledge of determinant in the definition of sign map. So, for example, this delta, so this comes from this particular matrix called Van der Waals matrix, so which is defined to be, so it is a matrix whose entries are some monomials. Okay. So, you take 1 x1, x1 square etc. x1 power n minus 1. So, this is an n by n matrix, and then 1 x2, x2 square etc. x2 power n minus 1 and so on. The last row is 1 xn, xn square etc. xn power n minus 1. So, this is your Van der Waals matrix. So, what one can prove, okay, using properties of determinant. So, the determinant of this V of x1 etc. xn is exactly equal to delta. So, this is what one can prove. Okay. For example, one way to prove is directly use the properties of determinant. So, you can see that easily the determinant of this V of x1 etc. xn, that is supposed to be a polynomial, okay, multivariate polynomial in x1 etc. xn. Okay. So, now if you take any ith row and jth row, so then you can see that if you replace, so that by okay, so xi equal to xj. So, for example, you can look at this ith row and then jth row. So, then you substitute xi equal to xj. So, then what happens? Then ith row and jth row in this V of x1 etc. xn, they become equal. Okay. So, that means, so they have two identical rows, both ith row and jth row they become equal. So, that means determinant of that V of x1 etc. xi etc. xi, that will become 0. Okay. That means, this xi minus xj, that particular polynomial, okay, that will be a factor of this V of x1 etc. xn. So, what I am trying to say, so it is easy to see that, so V x1 etc. xi etc. let us say I is given to be less than j. So, then you replace xj by xi again etc. xn. So, then it is easy to see that the determinant of this is exactly 0. If you call this is some polynomial in x1 etc. xn, then you can see that, so from this observation p of x1 etc. xi etc. again xi etc. xn, this is going to be 0. So, that implies what? That implies xi minus xj divides this polynomial. Okay. So, p of x1 etc. xn. Of course, I am using so much information that you use in higher algebra. Okay. For example, you need to know that this whenever you substitute xi equal to xj, if it is 0, then that xi minus xj, that will be a factor of this polynomial. Okay. This is something, if you do not know, you will be actually seeing this proof in some higher algebras. Okay. but this is the best way to actually prove that the determinant of this v of x1 etc xn is delta. But now since this is actually a factor, okay, so these factors are all relatively prime, okay, that is also there. So this xi minus xj, so when I and j varies over 1 to n such that I less than j, so these are all relatively prime factors. So in particularly the product of them, product xi minus xj, 1 less than or equal to I less than j less than or equal to n, this is going to divide your polynomial p of x1 etc xn. So I am actually hiding lots of results under the corporate, but you can see that, okay, so at least some outline of the proof is there in the in this okay. So but anyway, so once you know that these are all relatively prime factors, so then the product of that should divide this p of x1 etc xn. So now if you compute the degree, okay, that is easy to do because this is just a determinant of this particular matrix v of x1 etc xn. So I will leave it you to compute the degree of this, okay. So here is the exercise. So what is the exercise? Compute the degree of this determinant v of x1 etc xn. So then you can see that that is going to be exactly the degree of this, okay. So the degree of this product xi minus xj is going to be exactly equal to the degree of this p of x1 etc xn. Now because both the degrees are same and one is factor of another, so when you take the ratio then it has to be some constant, okay. So now you can see that both of them are actually monic polynomials, the highest degree term, okay, that will have constant coefficient 1. So by matching that constant coefficient you can see that they must be same, okay. So that is the outline of the proof. So this p of x1 etc xn divided by this product xi minus xj I less than j, this is going to be some constant. Now that constant has to be 1 by comparing the like some terms there, okay. You can just compare, for example, the highest degree term. Okay, so this tells you that this van der Waals determinant has this van der Waals matrix has this determinant which is delta. So that means for example, all the properties that you see for the sign map, that is reflected in this delta, okay. That is why you can simply take this delta and then work with this and then define the sign map. Okay, now let us see how one can define the sign map using this delta, but before that let me just give you one example. So for example, if you take n equal to 4, then the delta looks as follows. So first you have to count everything. So you can start with the 1. So then 1, 2, 1, 3, 1, 4, they are the tuples that will be involving I equal to 1. Then you can see that these monomials will be appearing x1 minus x2 and then x1 minus x3 and x1 minus x4. Then you can change I equal to 2, then you will get x2 minus x3 and x2 minus x4, and then you can change I equal to 3, then x3 minus x4. So this is your van der Waals determinant, okay. So now you can see that if you start with any sigma coming from Sn, then you can make this sigma to act on this delta. Basically you can act it on, you can make this to act on this polynomial, of course. So then what you get, that is what important, okay. What will be the final answer when you actually permute these variables using this sigma, okay. So for sigma in Sn, you define what is called this sigma of delta. It is a new polynomial which is obtained from delta by permuting these xi's, okay. So this is just defined to be again the product, you take x sigma of I minus x sigma of j, okay. Again the the indices run over from 1 less than j, where 1 and j are coming from 1 to n. So, this is your sigma of delta. Okay. So, now what one can prove, okay, here is the climb. When you take this sigma of delta, then it differ by delta by a sign plus or minus 1. Okay. So, the sigma of delta is exactly equal to plus or minus of delta. So, let us do one example and then you can convince yourself that this is the case. So, when you take again n equal to 4 and then apply, for example, this cyclic permutation, okay, 1, 2, 3, 4, let us see what we can get. Again take n equal to 4 and sigma to be the cyclic permutation 1, 2, 3, 4. So, then what do you get? So, this is going to be 1, 2, 3, 4. So, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 1. So, this is your sigma. So, then what is your sigma of delta? So, then you can see that. So, 1 you replace by 2. So, it is x2 minus x3 and then x2 minus x4 and then x2 minus x1. Okay. So, then you replace x2 by x3. So, it is x3 minus x4 and then x3 minus x1. So, then finally, you replace 3 by 4, it is x4 minus and then x4 by x1. Okay. So, this will be the new polynomial, but you can easily see that, okay, when you apply this sigma. So, either the sigma of I is going to be less than sigma of j or sigma of I is going to be greater than sigma of j. So, only these two things can happen. Okay. So, from this, by separating them, you can see that. So, you will be getting only. So, whenever they are not in the correct order. So, for example, like this, when they are not in the correct order, you can switch the order and then you can make it correct. Okay. So, for example, you can see that this x2 minus x1, it is not in the correct order. So, you just switch and then make it correct order, but you will be paying a cost, you will be paying that cost, that is minus 1. So, then if you rewrite, you can see that from this you will get 1 minus 1 and then this is in the correct order, 2 3 is fine, 2 4 is fine, 3 4 is fine, but 3 1 again. So, this is not in the correct order. So, then you have to switch. So, you will be actually paying extra cost. Similarly, this is also not in the correct order, which is x4 minus x1. So, you have to pay one cost. So, then up to this you can see that you get back delta. So, that means sigma of delta is exactly minus delta. Okay. But as a permutation, you can see that what will be the sign of sigma. So, the sign of sigma, one way to compute, you write it as product of transpositions. Okay. So, you can see that sigma can be written as 1 2, 1 3 and 1 4. Okay. So, now it means sign of sigma will be minus 1. Okay, let us check whether this is correct. So, 4 goes to 1. So, 1 goes to 3, 3 goes to 3. Sorry, 4 goes to 1, 1 goes to 3, 3 goes to 3. Okay, maybe what I wrote not correct. So, 1 2 1 3. So, 1 goes to 4, 4 goes to 4, 4 goes to 4. So, this is indeed 1 goes to 4, but we need 1 goes to 2. So, I should write it in the reverse order maybe. So, 1 4, 1 3 and then let us say 1 2. So, then you can see that 1 2 3 4. So 1 goes to 2, 2 goes to 2, 2 goes to 2, and then 2 goes to 1, 1 goes to 3, 3 goes to 3. So 2 goes to 3. So 3 goes to 3, 3 goes to 1, and then 1 goes to 4, and 4 goes to 1. Okay. So this is your 1, 2, 3, 4 permutation. So indeed the calculation actually matches with so what we are promising. Okay. By using this delta, you can see that whenever you apply sigma to this delta, some plus or minus going to come. Okay. So now we will actually claim that this sign that it picks up, it will be exactly the sign of sigma. Okay. But before that, how are we going to proceed? So let us first convince we always get some plus or minus. Okay. So that is easy to convince. So you can see that delta contains one factor. Okay, these are all the observation. So delta contains one factor xi minus xj for each I less than j. Okay. And then the sigma is indeed a bijection from in to in. So this is just a bijection. So whatever it does, it is going to just permute the indices. Okay. In particularly given ij, so given I less than j, either we have sigma I less than sigma j. So this is indeed, you can think it as it is in the correct order, or sigma I is going to be greater than sigma j. So it is not in the correct order. So whenever it is not in the correct order, you have to switch. So basically you can define these pairs ij, so which is coming from in cross in, such that okay, I is less than j, but sigma of I is indeed greater than sigma of j. So this is where something wrong happens. So that you call it A sigma. Okay. So this is actually has some very important motivation. This set is called the set of inversions. So basically what it does, so the sigma spoils the correct order. It actually just switches the order. So those tuples, you call them the set of inversions. So then it is clear from the definition that sigma of delta is going to be minus 1 power the cardinality of A sigma delta. Okay. So because you can see that sigma of delta is going to be what? It is going to be product x sigma of I minus x sigma of j, I less than j, where sigma of I less than sigma of j. So this is one such product where the order is correct. Okay. So then times you will have another product where x sigma of I again minus x sigma of j will be there, I less than j will be there, but sigma of I will be greater than sigma of j. So this is the another order. Okay. Only these two things can happen. But then if you take this second part, so this is something you have to switch. So if you switch this, then what's happening, then sigma of delta, so this is let us say the first one, that one will appear as it is. So this is the first one. So the second one is going to be product x sigma of j minus x sigma of I, then you will get minus 1 here, where I less than j, sigma of I greater than sigma of j. So each switch you get 1 minus 1. So that means, so when you take them out, you will get minus 1 power the cardinality of A sigma. But sigma just permutes all the indices. Okay. So once you arrange it in the correct order, then you get back delta. So there is no issue with that. So then sigma of delta gives you exactly some sign times delta. Okay. But what we are going to claim, okay, this is the claim that this sign of sigma that we have actually defined, which is determinant of tau sigma, this is going to be exactly equal to minus 1 power cardinality of A sigma. Okay. So, this cardinality of A sigma, this is the number of inversions, okay, that is the cardinality of the set of inversions. So, this also plays very important role. So, this is the cardinality of I comma j, which comes from in cross in, where I is less than j, but sigma of I is greater than sigma of j. Okay. So, this number plays very important role. For example, when you want to think this symmetric group acts as a Coxeter group, then one can talk about length function of that given element with respect to the Coxeter generators, and the set of inversions they play. So, basically the cardinality of this will count exactly the length of that given element with respect to the Coxeter generators. But those things are aside, but even in symmetric group theory itself, they play a very important role, like when there are some combinatorial invariants that are associated with this given permutations. So, they mostly involve these things. Okay. So, I will stop here, and we will see the proof of this fact in the next class. So, this actually kind of first of all introduces sign maps in some other way, and it also gives you another characterization of sign map in terms of this set of inversions. So, that is why I am interested in doing this. Okay, we will stop here, and then we will see a proof in the next class. Thank you.